Okay, so next up we have Jim Phillips. Jim is the lead developer of NAMD and has been for quite a while. He works down at the Beckman Institute at the University of Illinois, just a few blocks over. And today he's been talking about charm and NAMD on KNL. So,
okay, thank you. So yes, not even a few blocks. I crossed the street, and I didn't even do that because I park right across the street here. But it's always good to be at this workshop. Today I'm going to give you a little of what we've learned from the new Knights Landing platforms. First, a little bit about NAMD. This is sort of a long-standing Charm++ application. We have a large number of users. We're funded by the NIH. We try to be user-friendly, in particular, partially enabled by Charm++. We sort of have one program that you can run on everything from your desktop and laptop at a workshop for small sort of toy problems to a local Linux cluster. And then at the largest scale, we're the most used code at TAC, for instance, and the widest used application on Blue Waters. So we sort of span the entire range of computation. There's a strong GPU acceleration effort that I won't be speaking about today. And we really try to preserve user knowledge across all of these platforms so we can hide as much complexity as possible, and this is free. And this goes through a long connection with PPL, Professor Calais, and Charm++. Going back over 20 years, we won a Gordon Bell Prize in 2002, and then Professor Calais and the late Professor Schulten shared a Fernbach Award in 2012. And there are continuing optimizations to improve the performance of NAMD. Since NAMD is sort of an older Charm++ application, we don't use all of the latest bells and whistles, latest bells and whistles meaning like this millennium in some cases. But we do view it as a parallel Charm++ with data-driven objects. We benefit strongly from that, the asynchronous method invocation, the prioritized scheduling, the measurement-based load balancing, and finally, a portable messaging layer so we don't have to build on top of whatever MPI library happens to be available on the machine. So this is really, the essence of Charm++ from a performance perspective, and then we have some of our own abstractions for programmability that are now supplemented by things such as char arrays and AMPI, as you've been hearing about. The essence of the parallel decomposition in NAMD is a hybridization of a spatial decomposition or domain decomposition. You can think of the data in which the atoms that we're simulating as these blocks, and the interactions between them are represented as objects, and we can independently schedule these objects. We start out with a very communication efficient, sort of neutral territory type method in the beginning, but based on the measured performance, they can be relocated by the load balancers. We benefit from the overlapping execution capabilities in Charm++. So if you look at a single time step going from top to bottom, the equations of motion, basically F equals ma from Newton, are integrated in the spatial decomposition. The coordinates of the atoms are multicast to compute objects, so we have sort of a non-bonded calculation as well as bonds, angles, et cetera, that represent the covalent structure of the biomolecules in water that we're simulating. There's also a long-range electrostatics method that is dominant in the field called particle mesh AWOL that is based on a 3D Fourier transform. 3D FFTs for really small amounts of data. I mean, for the largest simulations we do, this is maybe a 512 cubed grid of data. Latency sensitive, but we're able to overlap this for the past 20 years with the more intensive non-bonded calculation. And then this is, of course, reduced, and we complete this every time step. We want to get this whole thing done in a matter of a few milliseconds or shorter. For the GPU, we took at first the most intensive part of it, which is the non-bonded calculations, offload that. Now we've offloaded for small numbers of nodes the FFT for the long-range electrostatics, and we're moving towards doing offloading of the bonded terms as well, simply because the ratio performance between the CPUs and the GPUs is getting more disparate, particularly on the upcoming Volta machines. So this is sort of a brief history of NAMD and the sister visualization program, VMD, showing where the science has gone. So basically, over time, parallel computers have gotten better, larger, and the systems that we've been able to simulate have also gotten larger. But what I like to point out is that these are not gratuitously larger systems. This is not throwing more atoms in a box, shaking it, and seeing what happens. This is not a larger domain. This is not finer decomposition. This is one molecule, one aggregate, one virus, one ribosome, one virus capsid. Many of these are not even complete systems. In particular, there's an entire shell missing around this. And this is basically following the trends in structural biology and biophysics, that if we want to keep up with what the experimentalists are discovering with the improving methods and provide input to that, we need to go to these larger scale systems that are really at the forefront. There are some people in our field who do very good work, who work on systems of this size or smaller, even on blue waters. Also good science. This is the direction we've taken. And NAMD does a quite good job with these large petascale class simulations on the large machines. So this is the full influenza virus, not merely the capsid. And this is actually an external user of the program from UCSD running on blue waters. We have some comparisons here for sort of representative, very large, and still quite large scales of systems. This is from SC14, but we can see scaling the benefit that we get from the GPUs on Titan, about a factor of 3 over blue waters, which is replacing the GPU with a second CPU, and then a more newer CPU class machine, the Edison Cray XC30. The one thing I like to point out here, just to brag about NCSA a little bit, is that the GPU-accelerated XK7 nodes of blue waters are effectively identical to the nodes on Titan. Same CPU, same GPU, same network. But blue waters, it has a smaller number of them, and it has a topology-aware scheduler. So when we run the same code, the same benchmark on the blue waters GPU nodes, we get better scaling than when we run the same science on Titan. So we are definitely seeing a benefit from that and an effect of the topology of the network. Again, there are a variety of projects using NAMD at this scale. So you recognize the viruses. This is something the Easter Bunny could suffer from. This is a relatively simple photosynthetic light harvesting complex. And the chemosensory array is what we like to think of as the bacterial brain. So if you're a bacteria, you need to sense your environment. You need to sense chemical gradients along your very short body while you swim and decide, do I keep swimming the same direction, or do I tumble and find a new direction? This is a mechanical computer that somehow makes this decision based on chemical inputs across the entire structure. And we're able to study this thanks to experimental methods and the performance of NAMD on the petascale machines. But we don't also only do these very large-scale structures. There's really been a renaissance over the past few years in using multiple copy methods. So if you've seen the partitions feature in Charm++, also referred to as replicas, and wondered what that's for, this is what it's for. By doing multiple coupled simulations of a small system, we can take simulations for, maybe a few tens of nanoseconds, a few hundreds of nanoseconds, and obtain detailed energetic information and structural information on processes that run into the milliseconds. Let's see if you can get this to run again. So this is a membrane transporter. There's a membrane here, perhaps a membrane in the cell, and we want to move this substrate from one side to the other side and control what moves in the other direction. A transporter lets you do that as opposed to having a pore, which things flow through freely. This is a large-scale, very slow, detailed transition in the structure of this protein, and we're able to model this. So coming forward in this, I was appreciative of the keynote where there was the discussion of how it's important to allow the scientists and the users to make changes without having to understand the whole parallel structure of the code. We go one step further, and we use things like TCL scripting to try and avoid even making them recompile the code. Because again, we want them to be able to run from their laptop to the supercomputer. Any innovations that they make, it would be great if they could bring that along and just run it on whatever optimized version they have. So this is one example. This is a more advanced method called milestoning, which gives you not only energetics, but timescale information. And simply by running a large number of simulations starting on one hypersurface until you hit a neighboring hypersurface along a transition path. This requires some flexibility in our runtime system because those different simulations could run for an arbitrary amount of time until they hit the barrier. And just to connect it back to the topic, this was an early science project for the new KNL nodes at Stampede. This is what's referred to as a hexameric molecular motor. This actually degrades proteins by pulling them through, driven as everything in the cell is by ATP. So we're able to model this using these advanced methods. We have a new release out. Oh, for Christ's sake.
Oh, that's not what you meant by new release.
We have a new release out, as does Microsoft. See, I'm so, it's a Mac. We don't have any of this crap happening. It's still PowerPoint. Okay, so we have a new release out, new capabilities. There's a new QMMM interface, extensions to various other features and performance, particularly on the GPU side, as well as the new KNL features. This was actually work supported by NCSA to say, well, what if we just want to simulate the shell of the Easter egg without all the water on the outside and the inside? Before we had some performance issues, we've been able to improve this scaling substantially. And then from the Charm++ side, we have a feature called collective variables, which is a massive library of different steering methods, but it was basically serial, and it was a serial bottleneck. Using the Charm++ SMP builds, shared memory within a process, combined with the CK loop feature, which is similar in spirit to OpenMP loop parallelization, we were able to distribute a lot of that computation on demand across the processors in a node and give sort of a factor of 2 improvement for a set of simulations where this was a bottleneck. So we continue to steer the development and features in Charm++ based on the performance issues that we encounter in NAMD. So you've all seen this slide or similar slides showing, the problem that we face is that the power of CPUs and the frequency and the single thread performance have all leveled off. The way the engineers are achieving improved scalability is by increasing the number of cores, and those cores aren't getting faster, so we have to adapt to this. GPUs are one direction, things like KNL are another. And at NAMD, we work very hard to be associated with the early science projects for the Department of Energy and other machines. So we are just now wrapping up the KNL generation of early science projects, both for Argon Theta, Nurse Cori, and then TAC Stampede KNL nodes, which I'll also be discussing. We have this year coming up the new GPU accelerated machines at Oak Ridge, and then recently approved our participation in the Aurora early science for the next generation Xeon Phi processor. These benefit not just the high-end applications, but also the low-end applications. So, and just to point out what this is, the Volta 1, this is molecular machinery of the brain. You can think of this as a very small version of the transistor of the brain. We know the brain works by neurotransmitters. There's a spatial relationship. People are mapping neurons. People can get signals for this kind of this, but there's no molecular level understanding of how the neurotransmitter release process actually works. that's what we would like to model. Okay, so Xeon Phi, a little bit of background. You either have read about this processor or you haven't. This is it. It has between 64 and 72 low power, low clock speed cores, much better than the previous generation Knights Landing. It's a standalone processor. You can see this is one core and there's a mesh network between those cores. Neighboring pairs of cores form a tile which share a level 2 cache and share their memory channels and everything else. Each of these cores has 4 hardware threads, so you're looking at least 256-way parallelism on this chip, although in comparison to the previous generation, you do not need to use hardware threads in order to achieve maximum floating point bandwidth. You do have enough instruction scheduling capability. The threads are there for your convenience to hide latency as you need it. 3 installations in the United States that we have access to: Argonne, NERSC, and Texas as the successor to the largest machine on the Exceed system. And we've had to address several challenges, some of which are ongoing. So the first item is, of course, we have these new 16-wide vector instructions. This is called by Intel AVX512. We worked with some Intel engineers to develop new kernels. They wrote some versions of the kernels with us using the Intel intrinsics, which I do not like because they are, effectively illegible and unmodifiable. So they basically showed us what the compiler itself can do if you write things the correct way, and based on that and some of their ideas for implementing the kernels, we were able to take a working kernel and, in the most straightforward manner possible, come up with a KNL optimized version. So there's a special flag to enable this at compile time, and of course you have to tell it to build for AVX512 for the mic chips, distinguished from the AVX512 that is coming on the traditional Xeon server processors. Alignment is important, and we make great use of this Pragma SIMD assert, which is very closely related and actually inspired the OpenMP SIMD pragmas. We switched to single precision. We're using a simpler form of interpolation for electrostatics, similar to what we do on the GPU. Rather than using interpolation tables for the van der Waals type interactions, we're now doing explicit calculations because those do not require things like error functions, and we have less memory bandwidth available per amount of floating point on the chip. And for special cases like interactions between excluded atoms, alchemical, basically all the bells and whistles that aren't used everywhere, we fall back to the old kernel. So we didn't have to re-implement anything. We only re-implemented the real performance critical. One highlight of this, AVX512 has improved gather instructions. You call it once, you don't have to recall it. It goes and does the gather. The hardware is not as sophisticated as it is on an NVIDIA GPU, however, but it is a benefit. So this is a simple example. This is what we call the pair list to pair list loop. So we have a list that we're iterating over here of list size, and we're trying to cut that down from atoms that are close to the cutoff distance to atoms that are inside the cutoff distance. So as long as the indices are ints, if they are 16-bit shorts, which we had done on the previous version because it shared saved memory, they have to be 32-bit. Then you can generate these gather instructions. And we're basically pulling elements out of an array of structures. So this is cache-friendly as opposed to a structure of arrays. It could generate gather instructions based on this. There is also a gather to shuffle optimization that it can do automatically but isn't beneficial. A little bit of math. And then we basically save all of the data that we've gathered and the data that we've generated in compact arrays so that when we actually go through the force calculation, we can do straight vector loads. So this was sort of one of the optimizations. KNL has a plethora of what are called memory modes. So one of the features I didn't mention before is it has this very high bandwidth memory. factor of 10 faster than the normal DRAM. So if you have a memory bandwidth limited code, you run it on KNL, you magically get great performance. You don't have to do anything. It's all in the memory, as long as you use the memory correctly. You have two choices, flat mode, in which the high bandwidth memory is exposed as a separate NUMA domain. So all your cores live on NUMA domain 0, and anything that you want in high bandwidth memory, you put in NUMA domain 2. If you were lucky enough to fit completely in that 16 gigs of memory, you can just say NUMA control membind equals 1 or preferred, and you get most of the benefit. Your other option is, since this chip does not have a level 3 cache, you can use the high bandwidth memory, either all of it or a fraction of it, as cache. The experiments people have done on these machines, it is pretty much, almost as good a performance, indistinguishable from what you get in flat mode with the correct NUMA control. It does some things correctly, but this is a direct map cache. So if you have two active pieces of memory that map to the same cache line, you could potentially get thrashing. You might not notice it on a single node. You might not notice it on 100 nodes. There is a real danger that when we run on 50,000 nodes on, for example, Aurora going forward, that you will definitely notice this. So this is a scaling impediment equally as much as it's a performance impediment. But for most applications that people have been able to test, it works great. When in doubt, use something called cache quadrant mode. There are these other nodes for dealing with the page table efficiently, sub-NUMA clusters, et cetera. We or anyone else really haven't observed a strong benefit from that. So those are your features. And because these modes have to be set at boot time, this is basically how the machine runs. We run, so in Charm++, you're familiar, there are a variety of network layers that you can use. So multi-core, which is SMP with a separate notice, single process, various network-based for TCP, GNI for the Cray networks, verbs, or the deprecated IB verbs for InfiniBand, MPI, which is there for portability, but it's the best we have for OmniPath at this point. You need to pick between SMP or non-SMP. If you use SMP, you lose one core per process for communication, but you get multiple worker threads. And finally, you have compiler options like ICC static, and we like to use no build shared with production just to turn off some of the extra code. General tips, we tell people don't use the MPI layer, but you can use it to leverage startup. The only reason you do use it is for OmniPath. If you have a larger simulation, you really want the SMP builds, and this applies to pretty much anything on KNL at this point. Setting processor affinity with these COM-map and PE-map options is very important for performance. And for scaling, trying to reserve one core for the OS, either explicitly on a Cray or just by leaving that free, prevents some system noise. So if we look at the two platforms that we're running on, 64-core processors at Argonne, 68 down at TAC. We use the Cray version with persistent messages in SMP. Versus TAC, we have to use MPI because that's the best we have for OmniPath. We're using 13 processes per node on TAC, only 7 on Cray, and I'll talk about that a little more lately, but basically this is because we need more communication threads because of the onloaded OmniPath model. And then we have this 2 options for how to set up PE map. And these are, of course, they look a little bit like magic when you first look at it. The logic's pretty simple. We want to leave one core free to isolate the OS nodes. Pairs of cores that are on the same tile share the cache, so we don't want to have the PEs that correspond to different processes or Charm++ nodes sharing one of these tiles and competing for those cache lines. But it's OK to split a tile between communication threads if we have to. We try to use 1 or 2 hypothreads for the PE cores. There's no benefit that we've observed from 4, and 3, there's really no case in which that would be beneficial. We need several communication threads per host. simply to drive the network communication for the large number of threads and to avoid contention within a process, fewer for Aries. And also, having multiple processes gives you multiple copies of the static data, which actually distributes better within the memory system. And finally, depending on the core count, you have different communications. So for theta with 64, in Riv 1 you got 63. We could go 9 processes, or we could go 7 processes. If you do 7 processes, you get a couple more worker threads for about the same amount of communication threads. Or for the same number of worker threads, you could have fewer communication threads. So this is dominant. And then we sort of spread it out. If you do for 4, then you can use an entire tile for each communication thread, which is why this is strided 16 rather than packed together. On TAC, we really need to go up to 13 communication threads. And you'll notice we're losing a good 20% of our performance in order to have those communication threads. So again, this is 4 or 8 cores per node. And these are the other options, which give you more worker threads, but less communication. This is what the performance looks like on theta. So this is just sort of comparing to the other machines we saw previously. This is the GPUs. As you can see, the KNL nodes are beating the CPUs like NERSC. They're definitely beating Blue Waters. Not quite as good per node as the GPUs. But you could argue, OK, what if that's per socket? In that case, KNL is the fastest performance we see per socket. KNL is a single socket only processor. And then you have to remember, however, these GPUs are 2 generations old. On Stampede, if we look at a smaller benchmark and compare this, so this is ALCF theta up at the top here, scaling quite well. Between 32 and 64, we switched from 2 hyperthreads to 1. Even with the 13 communication threads on Stampede, we do not get anywhere near as good a scaling. So first of all, if we run on one node and we have a single process with multi-core, we get, again, 20% higher performance because we're using all of those threads. You lose that just to go parallel. So you could draw this line like this. To be fair, we'll put it here. Here between 16 and 32 is when we switch from 2 hyperthreads to 1. And after that, we get one more little bump, and 64 is sort of as wide as we're allowed to run on this machine. Still better than, again, the older cores, but we have some significant scaling issues. And again, this is due to OmniPath. One little thing, we did get access to Cori, which is much larger than theta. And we said, OK, let's try 1 billion atoms. How does that compare? Well, we can do it. And again, we're sort of tied with GPUs. There are various inefficiencies in this right now. And if you look at it per node, or per socket, again, of course, KNL is coming out on top. But the target platform for the simulation is about 10 times to 100 times faster over the next 5 years. Just to wrap up, AVX 512 with Intel compilers works great on KNL as long as you know the limits and the tricks, and you want to watch for bugs. The high bandwidth memory, you can use cache mode, although you have to be aware that there may be scaling issues. You do need an SMP build. You do need to think long and hard about where to put your PEs, where to put the communication threads. Aries works pretty well, 7 processes per node. OmniPath is really where the extra work is required, both for KNL and for the other systems. What's unique about OmniPath is they have what they call an on-loaded architecture. So they let the CPU do as much of the work as possible and have a much simpler and cheaper NIC card. That would work great if you had very fast CPU cores from 5-10 years ago relative to the card. As you start putting on more and more of these slow cores, this architecture becomes more of a bottleneck. And in particular, we're hoping that specializing to the PSM or OFI network layers will let us do a little bit better. With that, thank you very much to all the funding agencies and centers and users and developers we've had over the years, and I'll be happy to take any questions.
Any questions?
Hey, Jim. Nice talk.
Thanks.
So you had said something about getting rid of the lookup interpolation tables, but then you also said you're using linear interpolation similar to CUDA. That seems like a contradiction.
We got rid of the interpolation tables for the van der Waals
Okay.
forces.
So you're still using that
Right.
for
So
electrostatics.
so they were still a benefit for electrostatics for now.
Okay.
But yeah, so there's much less of it, and there's much less
But it
memory
seems like that would
traffic.
still kind of be a bottleneck for doing your vectorization.
With the gather instructions, it does work out okay. So
Okay.
there's enough latency to balance that out. So if they did not have the gather instructions, then it would be more of an issue.
Okay. And so also you had mentioned using the the pragma approach versus the intrinsics, and I wondered if you just compared the two approaches performance-wise. Do you lose something with the pragmas that?
It's pretty close. I think we got further with the pragmas than we did with the intrinsics, just because we could have more iterations. There's nothing. What we would do with the intrinsics you can do things like what they call a gather to shuffle operation, where if you have a structure of arrays, you can load and do movement in register, but the compiler can generate that now. So what we're hoping is that as the compiler continues to improve, we can sort of massage the code to be friendlier to the compiler and let the expert software take care of that.
Okay. Thanks.
So my question was very similar to that last question. So at the moment, how much is sort of using intrinsics versus sort of
It's
writing the code to the compiler?
It's all SIMD pragmas at this point.
So, talking about OmniPath, if I understood your last bullet point, you're saying that you hope to get better performance by going back to an older communication layer?
No. These would both be new. So OFI, we have a version contributed by Intel. It's just not beating MPI. We believe the reason for that is that OmniPath is designed to run MPI programs. So the amount of disconnect and reshuffling between the MPI API and the PSM2 API that is sort of the lowest level for OmniPath may be very thin. We're hoping by going to PSM2, which is sort of the native OmniPath, that we could do a little bit better than MPI. But it may be part of the structure. But no, these are not older network layers. These would be forthcoming.
Okay, thank you. Do you know what the timeline for that is?
Depends on community interest.
For the PSM2 port? Or for the OFI, it's a long, complicated story. I'll tell you over the lunch. But basically, it's actually an interesting trade-off when someone says, "Hey, we have a layer for you. We just implemented it and it works fine. What do we need to do?" We spend a lot of time trying to integrate a submitted layer, and it's not worked as well. Going to PSM will be a lot of thankless type of work, and we're wondering how much performance benefit we're going to get. So we're going to have to carefully estimate the work and the benefit we'll get out of it. If you have input on the potential benefit we could reap, that will be useful. No, thankless work is one of the things that Cham works is for, so maybe we'll do it there, but not clear what the benefits are yet.
I'm wondering how NAMD addresses the GPUs. What part is Charm doing, and what part are you doing?
So at this point,
Just at a very high level.
right. So NAMD's been doing GPUs for 10 years now, so we really rolled our own solution, and the Charm++ layer is now caught up to that. The real challenge that we faced is basically aggregation. So we have a lot of these small objects on the charm side that are far too fine-grained. They map to a single CUDA block.
Right.
They do not map to a kernel, and the ratio of performance to overhead of kernel launch is not going to get better. So that aggregation was really the challenge. And linking that aggregation to the distributed control that's in NAMD using things like the charm++ threads. That's the challenge. So we're not using the charm++ tools right now because we have our own, but hopefully there are better solutions to those issues that are being inspired in the charm++ tools.
Thank you.
Next we go.
There first. Okay. So you talked about using the Intel compiler. Or Clang at all using?
No, I've wanted to get something working. Yeah, I mean, I would fully expect that the Intel compilers would be the best at writing code for their own processors, particularly, the Intel compiler team has well-advanced access to the architecture and the performance models. So I would trust the Intel compilers for this. In particular, working with the Intel engineers, we can complain about the Intel compilers and they expect them to get that fixed.
Right.
But I have nothing evidence-based to say about GCC or Clang.
Okay, thanks. Yeah, it's just, my experience has been
Yes, that is. We try to be even worse at keeping up with the C++ standard until Sanjay drags us forward. Well, Phil drags us forward, but we stay away from the edge. Okay. We had a couple. Oh, I did call you out, didn't I?
Yeah. So Intel has actually gotten better about keeping up with the standards. They've got full C++ 14 support. Well, they claim to at least in 17. Okay, I'd be interested to hear what doesn't work because it may get in our way.
enable if invariant constructor templates.
Okay,
Okay.
we'll take a look. Thank you.
What they say.
So I think we should move on, but I just wanted to say one quick thing that remember Jim and John Stone are kind of pioneers in the GPU world. They're one of the earliest people to work with GPUs with me and with NVIDIA. And so it's fitting that they are ahead there. But I have a question there, but I think we are way out of time, so we should postpone that question.
Okay, so yeah, if you have any more questions, we can ask them later during lunch and things like that. But let's move on to the next speaker. Let's thank Jim one more time.
I'm going to respond to that question. I think Intel's actually building a Clang front end. So once they have that, they're going to have full 14, probably 17 support. So that's what I hear.